Well, if we leave the problems related to the exam aside, if we can, of course, then we can, it means that we can start and we can continue with the distribution systems. Now, today, we're going to see paper by Karabakal, which is in 2000. And I will also talk about the other paper, which is not required but recommended, because I think there is sort of a natural natural way of going from this paper to the other is vendor managed inventory, and I will talk about vendor managed inventory for a while. Okay, now this paper is actually is interesting because it is a report of an application, and basically this is the type of applications that we are looking for in YAD, Yönelim Araştırması Derneği Uygulama Ödülü. Okay, we have sort of a prize, and the purpose of the prize is to get out these type of applications in the field. And this paper is published in Interfaces, and Interfaces usually publishes papers in this form where you have a lot of description in the text, and all the technical material, as much as possible, is placed at the appendix. And the work is actually very similar to the other distribution systems that we have seen, but there are some particular issues which is dealt, and that's the reason why we are considering this. This is a study done at Volkswagen of America. I don't know the current situation of Volkswagen of America, whether they exist or not. But the issue is that this study contained a number of issues that we mentioned, but were not able to see in a single model. On one side, we are going to see the location problem, location decision problem, where should we locate the distribution center, and so on and so forth. On the other side, we see a relatively detailed model of the consumer behavior at a dealer. Okay? Of course, how are we going to put these into a certain model is not very certain, and then they propose a heuristic method, which is very reasonable, and there are a number of other models that uses the same heuristic idea. Basically, what you do is you use a mixed integer program on one side to decide on the locations, and then you evaluate the performance of the mixed integer program in a simulation where you can take into account customer interactions at the dealer level. And then you take certain performance measures back to the mixed integer program, which is obtained by the simulation results, and use this procedure until you have some kind of a convergence. Of course, proof of convergence and so on is practically impossible. But on the other hand, we know that these type of problems are going to have reasonable, we have reasonable reason. It is very reasonable to expect that the result is going to converge if you can do sufficient number of runs of this procedure. So this is the main reason that I wanted to have this paper in, because it takes different issues into account, which are usually modeled separately in the literature. Okay, now, and what they do is they start with discussing the distribution system ideas, which is more or less true. The distribution systems follow the Ford example in the US. And the main reason for Ford creating this distribution system was to be able to sell the cars ahead of customers buying it. So in other words, the previous understanding was the manufacturer would manufacture the automobile and sell it to the dealer, so that there will be enough cash flow coming to the factory, and the factory would work so that, because the cash flow is consistently coming. Now, what happens to the dealers or how they create the money was not a concern in the beginning, because you had a lot of people with a lot of money to become a dealer. Automobiles were very popular. But on the other hand, when we come to 1990s, things are getting now more complicated. Why? Because basically when the system was created, it was 1930s. There were no economies of scope, which means that there were only 1 or 2 brands of cars which were available. So buying them and storing them in a car dealer was possible. Whereas in general, some numbers are given. I think on the average, the sales of Volkswagen in the US were 30 automobiles per dealer on the average in a month, okay? And moreover, if you take into account the number of different versions, options, so on and so forth, it was much larger than 100. So what does this mean? Even if it is 100, if you really want to have one version available at any time at the dealer, okay, you have to have at least 100 autos, at least 100 automobiles in a dealer, which means that you are only selling 30 per month, and this means that you are going to have a huge investment in automobiles in a car dealer, which is not very reasonable actually, because if this is the sales, and the inventory turnover rate will be extremely slow. So, of course, given this situation, the dealers are going to fall into financial problems, as expected, and as a result, the automobile company would not be able to sell the automobile. You see, if you have unwilling dealers, if you have no available dealers, then you won't be able to sell automobiles. So, basically, as a result of this, the distribution systems in 1990s started to improve in the sense that more protection was brought in for the car dealers. Okay, so this is more or less the story behind the study. Now, of course, at this point, Volkswagen of America decided to apply the following policy. They said that we are going to have a 48-hour policy to take the car to the dealer if it's available at the distribution center. So, which means that the distribution centers are going to satisfy the demand for the dealers, keep a lot of stock, and so protect in a way the dealers. So that was the improvement which was brought. But how are we going to decide on the location of these distribution centers to make sure that we are doing everything correctly? So this is more or less the problem that we want to solve. So we are going to take into account location decisions. We are going to make location decisions, taking into account customer choices. Now, I will talk about what we mean by customer choices in a little bit more detail. We are not given a very clear idea of how this was modeled, but we understand that there is some kind of a customer flow cycle, and which is, I think, modeled in detail via simulation. So this is basically mimicking customers. Actually, it turns out that auto companies have this type of data available coming from the dealers. And this is what happens. Now, number one, a customer comes, has his or her first choice. So we are going to call it first choice. First choice is the automobile which the customer is asking for. Now, if first choice hits at the dealer, okay, this is something positive because it means that we are not going to lose the customer. Now, first choice may hit at the distribution center. In that case, there might be a possibility that the customer would leave because the customer may not be even willing to wait for, let's say, 48 hours. And it might be coming by the dealer trades. So here we see the idea of dealers trading with each other. So you have an auto dealer, let's say in Eskişehir, I have my auto dealer in Ankara. Okay, and the customer comes, first choice is not available here, but I see that it's available at Eskişehir. I buy it from Eskişehir. Okay, so note that like it is going to be available in a very short time. Okay, even you can have it at the end of the same date. So what you have is you have different probabilities of customer accepting these choices. Probably this is going to be 100%. This is going to be a little bit less depending on, and this is not going to be something that the dealer would really like to have, because probably the profit is going to be shared with the other dealer. But this is another possibility, and the customer might be willing to stay if these are possible. Now, if this doesn't happen, what happens? Then the customer might go to the second best or second choice, and second choice is available at the dealer, so you're set. Okay, so it means that customers with a certain probability, if they cannot find their first choice, would go for their second choice, and if it is available, you're going to have a nice hit. And or there will be sometimes some customers who are willing to stay for the automobile which is going to arrive from the factory. So what you do is you really look for something special. So you order that automobile and you are willing to wait for 2 months. Okay? So another one is direct factory orders. These are usually the customers who know what they are buying. They really say that this is what I want, and I know that it's not going to be available, and I'm willing to wait. And I'm not going to go for any other brand or any other makeup of the same car and so on and so forth. Okay? This is usually what happens with old Volkswagens. Actually, you have this Beetle, and everybody wanted to have the Beetle. Now, of course, the other remaining choice is lost customer. So you see here from the customer flow cycle that there is a certain probability that the demand is going to be lost. Now this becomes important because this is not back ordering demand. This is a lost demand, which means that the standard, remember the standard models, location models, are taking a certain demand into account, and you are locating the facilities according to that demand. Whereas in reality, we know that the customers with some process are either buying or not buying. So there is a possibility of losing that demand. The market is there, but because of your service, you are not getting that demand fully. So it means that if you give a certain location decision, okay, the lost sale that you are going to have is going to change your real demand. Your demand is going to be lower. Now, what's the meaning of this? The total cost that you are going to incur for transportation is going to be less. And at the same time, the profit that you are going to get is going to be less. So if you knew that ahead of time, if you knew that you were going to lose those customers, your original choice of locations might have been different, of course. So this is one of the things that we are going to put into the MIP model, mixed integer model, update the mixed integer model, and see what's happening. But eventually what we want is we want the mixed integer model's total demand to be consistent with the total demand that we satisfy in simulation, or in the other model actually. So this is more or less the thing that is going to be done. Now, of course, the lost customers are going to decrease the total demand. So as a result of that, what are we going to do? We are going to transport less. But how are we going to do that transportation? It's not very clear. So what we have is we have the so-called transportation load factors. Now, what do we mean by transportation load factors? This load factor is going to be a number greater than 0 and less than 1, less than or equal to 1. Well, it can be 1. If it is 1, it means that we are talking about full truck load. So that corresponds to 10 cars in a certain truck. Okay? But there will be some occasions where if we really want to satisfy a customer demand, we might be carrying the automobile alone in a truck. So we might have a single automobile in a truck. We are still paying for the transportation amount. Or we might have more cars in a truck. So the load factor is the average fill rate of the trucks that are used. So if I make it, I will show it a little bit in a more, well, I will give the formulation, but the idea is that if this transportation load factor is 1 and you are carrying 100 automobiles, that will correspond to 10 travels, whereas if the load factor is 0.8 on the average, it is going to be 100 divided by 0.8, which is going to be, let's say, 14 travels. So the transportation cost that you pay if the average load factor is low is going to be more, because you are having empty trucks going to the destinations. Now, again, why do we have this requirement? Remember, in a previous paper, we have seen that we are trying to fill the trucks, whereas here, we have this 48-hour policy that we want to satisfy the customer from the distribution center so that we still have the customer there, first choice. And in that case, we might not wait to fill the whole truck. So on the average, then your truck is going to have some load. Note that this load factor is a function of how you stock items in different dealers and in the distribution center. So another factor, and it's of course a function of the lost sales as well. Because you might make good plans, which is going to work if you are going to satisfy all the demand. But if a part of the demand is not satisfied, this is going to decrease your load factor as well. Okay, so this is basically a sign, or in a way, a proxy that shows efficiency of our operations with respect to the policies that we have. So now we obtained the two things which are going to exchange from simulation to MIP. We see that the demand is going to be, we have to keep track of the demand for a given location in the simulation. And that should correspond, then we have to update the demand that we use for the mixed integer program. And similarly, load factor is going to be an outcome of the simulation, depending on the customer choice random factors. And of course, then we should update our mixed integer program with that load factor. And we're going to see how we're going to do it, actually. Okay, so this is more or less the idea. Now, let me give the picture of what we are doing. Now, here we run an MIP, mixed integer program, which is very similar to the location problems that we have seen up to this point. Okay, so it is nothing different than that. You can have a coverage type problem, or you can have a fixed charge problem. It's not actually clear which one they had. They had, I think, both of them. Okay, they use any possible combination of those. I don't know. It's not clear from the paper. But you have a mixed integer program which purely acts on finding the best locations for distribution system, given the number of distribution centers, given a certain demand to satisfy, and given the load factors that we need to have. Okay, so the input that we are going to have from simulation will be, number one, planned sales volume, And here we're going to have truck load factors. So this is going to come from the simulation. You see that in general we consider that we are going to satisfy a demand. Remember, in location problems we always say that we are going to satisfy the demand. But the idea is that given a certain location structure, location network, okay, you may not be able to satisfy all the demand. So you have to correct that. This is the reason why this is going to be an input. Okay, then we run the MIP. What do we find? We find the location policy. Let's call it the location policy. It simply gives us the locations of the facilities. By the way, the facilities are capacitated. They have different types of facilities. So you can model anything you want in the MIP. And location policy comes out. Now, the question is, if this location policy is same as before, the previous location policy, then you stop. Because this is basically something that we're going to do. If yes, you stop. If no, you run the simulation. Now, what the simulation model will do is simply, it will take into account the dynamics of customers coming in, the lead times, okay, the stochastic issues like the customer's behavior, so on and so forth, into account. As a result of that, you are going to have, let's say that you do the simulation correctly. You have some performance measures. Like cost, customer service. Of course, you can count the number that first choice hits at the dealer, so on and so forth. I mean, you have a detailed service concept here coming from the customer flow cycle. Now, as a result, of course, you are also going to obtain the realized truckloads or truckload factors and realized sales. Okay? It is also going to come from the simulation, given your location policy. Now, basically, this is going to become the new input for the mixed integer program. Run the mixed integer program again and continue until you have a stable location policy. Okay, now we are given very little information about the details of simulation. So we don't know the type of uncertainty that we have here in the customer flow cycle, or the type of uncertainty that we have on the transportation times. They also mentioned that there is some kind of uncertainty in the transportation times as well. In other words, they also take, I feel that they also take the transportation times as random variables. But we are not given any information. But you can see that you can add a lot of things here, and it's not going to change much. Basically, this is a simulation, and given a location policy, you are simply obtaining values of the performance measure and some cost and customer service values. And this is going to be a feedback to the mixed integer program. Now, what do we have in the mixed integer program? Okay. Now, if you look at the objective of the MIP, mixed integer program, you have two places where these two factors are considered. Now, number one, in the objective function, you have a term. So L sub j is actually defined as the load factor in, I think if I am not mistaken, in, what was J? J was, I think, market, okay, in market J. So you have a number of different markets, okay, so you have sort of distributors, and around this you have markets. So this distribution center is serving all these markets. So for each market you have a load factor. Now we can see that the load factor is going to be for the market, because if we're talking about a small market, then the load factor is expected to be lower. Okay, so given this, so the term that takes into account the transportation cost is something like this: total volume shipped divided by Lj times T1 plus T2 Mij. So this is basically the transportation cost. So in general, if the load is, let's say, 10, or let's say 8, I may make a mistake on, let me see. Okay, I think load factor is not in between 0 and 1. It is in between 0 and 10. Okay. So it is not actually, it's a matter of scaling. So what happens is that if you have a total volume shipped, let's say, 100 in a given time period or in a given year, and if the load is, let's say, 10, it means that you are making 10 shipments. If load is on the average 5, it means that you are making 20 shipments. So this is the shipment cost. This is the fixed cost of shipment. So regardless the miles that you make with the automobile, you are going to pay this amount. And this is going to be cost per unit, or cost for miles traveled. Okay, so you have two portions of the transportation cost. One cost is like basically you have to hire some people to do that, and truck, this is a fixed cost, and this is a variable cost. So you see that you multiply this with the total number of trips that you have to that location. So it's a very detailed model, but in a way, if you give me what an average LJ is, then this is only going to become, this is going to be some kind of a fixed cost depending on the total amount shipped. And then here you have variable cost coming for each mile that you traveled. Now, again, key is if you give me the demand, I need to satisfy the demand in my MIP. Okay? So this part is going to be a constant. Whereas I know that in simulation, the realized sales should be what I have to write here. Okay? So what I do is I correct the realized sales and LJ factor after simulation. Okay? So this is basically more or less what is done. Because again, let me repeat this. The total volume shipped is going to be equal to, eventually equal to the demand. Demand that you satisfy actually, equal to sales. So what is changing here is actually the numerator is changing, because basically you may not be able to satisfy all the demand. And the denominator is also changing because of the efficiency that you have on the road. So as a result of this, what you have is you have this cost coming into picture in MIP. Okay? And you are solving the MIP, and you stop the MIP until your policy is sort of stabilized. Okay. Now, they talk about the solution. The solution turns out to be that what they do is they increase the number of distribution centers that they allow to be opened one by one and do the analysis accordingly. So first, I thought that they were doing a coverage type of a problem. They have the formulation at the back, but I don't think that they pursue that direction. In other words, they simply restrict the number to be opened and then increase that, see the effect of that, and propose one of those solutions. So this is actually what they do, and you can see that. You can see how this kind of a methodology can be applied to any problem. Okay? Usually what you do is you verify the location policy in a way in a simulation environment in order to represent certain norms which were not available, which cannot be modeled in MIP. Okay, any questions on this? Now, this type of modeling has been used a lot in healthcare problems, where, for example, you are trying to locate the ambulance services, or fire services, and what you do is you decide on a certain structure. But of course, you have different seasonalities in demand for these type of services. It's not very stable. Here also they have seasonality, by the way. And so what happens is that you want to make sure that the locations that you opened is going to satisfy the actual demand. So what you do is you run simulations, and you have very strict rules with respect to the precision that you want to obtain in the results of the simulations, because simulation is basically not a very straightforward tool. If you have to know what you are doing with a lot of stochasticity, variability, and so on. And so once those rules are set, then you can try different locations and make sure that the requirement that you start with in the mixed integer program is actually satisfied in a dynamic environment. So simulation has been used for that. So in those type of studies, what the simulation is going to bring would be simply a constraint on the response time. Okay? So in simulation, you obtain, for example, remember the coverage problem? Okay, we were talking about a certain distance. So what you would obtain from the simulation is that distance. So we put that distance into a mixed integer program, the coverage problem, and solve it again. Okay? And basically, after some time, we are going to have a convergence. So this is I think, a nice tool to remember if you are solving a practical problem. It doesn't have much theoretical insight, because basically you never will be able to prove that this type of a process is going to converge to a solution. Okay? You cannot prove that, basically. But I think it is a sensible way of doing things if you really want to show that it has the effect that you need. It considers all the factors that you want to have in this problem. Okay, any questions on this? Okay, now what is special about this work is we have two things which are special about this work. One of them is methodology-wise. The approach which is used makes a lot of sense because you have a lot of stochastic nature that you want to consider in a problem, and you also have a very open location type of a problem where you need to solve a mixed integer program. Okay? So you have both worlds there, and you have to have a methodology which is going to solve that problem. Otherwise, if you don't apply something like this, then one part is always going to be missing. This is the reason why I would usually tell the students who are making projects and so on, they usually approach the problem saying that, oh, this is an optimization problem, let us select that. This is a stochastic problem, let us not select that, and so on. So this is the bias that we have. Whereas if you have a real problem, actually, you would probably require to use both sides of the world. So you cannot say that I am an expert in integer programming and I can do consulting with that. No, actually it turns out that you cannot, because you have to think about other factors as well. Even if you are doing some theoretical work, you need to understand that these effects are there and you have to take that into account. There are other ways of taking this uncertainty into account or location policy into account. But I think but as a bottom line, you have to understand that you usually, as engineers, solve a problem. Okay, so solving a problem may require anything, and you are expected to know that. Okay, so this is number one lesson. Number two is the idea of VMI, vendor managed inventory. Now here we see an application of the vendor managed inventory idea. Because what Volkswagen is doing is basically, Volkswagen is, from the central office, is deciding on what to do for the dealers. Note that the dealers are simply out of consideration up to a certain extent, because they only give some orders, but the way that the orders are satisfied is more or less decided at the top level. Of course, the dealers still have some independency because they can order different types, but they can also find out the effect of ordering different types on their performance. Okay? So this is more or less a primitive vendor-managed inventory where the central organization sets certain rules, and according to those rules, the retailers, the dealers, are going to give orders or satisfy their customer demands. So the flow cycle, for example, the customer flow cycle, is what the dealers have to follow. In other words, the dealers have the obligation of persuading the customer that it might be available at the distribution center, so let's check for that. Or the dealers are responsible for talking to the other dealer for a possible trade. Okay? So all of these are factors that will affect the dealers, and this is sort of, as I said, a very primitive vendor-managed inventory where you don't have a contract, but you try to sort of intervene with certain things related to the dealers. Of course, in vendor-managed inventory, what do we have? In vendor-managed inventory, the vendor is going to control the inventory, completely control the inventory of the dealer. Now, our system, the current paper, actually allows for that. But we are not given very clearly whether, for example, Volkswagen is always fulfilling the orders of the dealers. In other words, the dealers may order certain things, but Volkswagen may be forcing them to take these specific cars. So we're not sure about that, actually. But you can see that you can use a tool like this for controlling the vendors, controlling the dealer's inventory. Now, next paper that we are going to see will be directly related to VMI. Okay? And I will explain the idea of VMI a little bit more at that point in time. Okay? With the specific policy that they consider. Any questions on this paper? It's very easy to read the paper, but certain things are missing in the paper, like the details that I was talking about. So don't panic, because, I mean, those things are on purpose missing. What you need to understand is, probably, you need to understand the relation between simulation and MIP. That's the key that, which is important here. So you need to understand this part together with the customer flow cycle. There is the notion of the customer flow cycle, not the details, because we are not, again, given a lot of details there. And so you can see that this is I think, the heart of the work which is done. Okay. Any questions? So let's take a break, and then we'll start with some issues of vendor-managed inventory.